Alright, today we're gathered here to talk about the modern atomic model. That's basically talking about atoms, the structure, what makes them up, and how it's relevant for a lot of these type of problems. So, I guess the last video was focused on some mechanics, namely stoichiometry, but today we're going to be talking about more useful items for kind of a theories or understanding why things happen in chemistry and even biology. Alright, so to start off, we got to talk about the atom first. When we're talking about the modern atomic model, we currently have three things to talk about for a given atom. But the one I would say bears the most relevance for most problems will be talking about the electrons and the protons. But the neutrons are also important, but we're not going to focus on the neutrons. And to start us off, we talk about the core, so the nucleus of an atom. So we have the atom. Oh, that's kind of small. Hold on. Alright, so we have the atom. And then the atom is basically consists of three parts, three components. We have the nucleus, which is the quote-unquote the hard part of the atom. That one consists primarily of the proton, and as well as the neutrons. Well, actually, I should do the other way around. Let's switch to colors. So we have the protons and the neutrons. The neutrons, they're called the neutrons because, you know, neutrality. They are assigned a neutral charge. So when it's a neutral charge, it's not given neither a plus nor a minus. Well, then we have the protons, which are assigned the positive charge arbitrarily. Protons and neutrons, and together they make up the quote-unquote the hard part of the atom, which is called the nucleus. Let's get the color right. Okay, so there's that, and then we have the neutron and the protons. Stay consistent, put an S right here. Yes, neutrons, protons. And again, together, these two things make up what we call the nucleus. Not to be confused with the biology nucleus. Nucleus. Wait, that's not right. Nucleus? I forgot how to spell. Well, we have nucleus. Let's just put this for now. This isn't spelling or English class, so this looks weird. Nucleus. Nucleus. That also looks weird. Let's delete that. I think this is correct. Yeah. Okay. Nucleus. Okay, that looks correct. Yeah, so the inner part of the atom of the modern atomic model, we have the nucleus, which consists of the neutrons and the protons. And again, the protons are arbitrarily assigned a positive charge. I'll just simplify it as plus with a symbol like this, plus charge. And then we have the neutrons. Those are absence of overall charge. And together, the nucleus, yes. And then we get to the fun part of the atom. That would be the electrons. So that one, we're not going to denote that. We're not going to represent that using discrete dots like this because, you know, that's not close to reality. So if we simply represent the atoms, if we represent the electrons as discrete particles, it's easier to see visually, but in terms of predictive capabilities, it's not very accurate. So to get closer to what seems to be the truth, we will represent the electrons as a cloud or a smear, or however you want to think about it. But think about it as not as discrete particles, but more as, kind of a big cloud that kind of aggregates around a given nucleus in certain spaces. So we'll do it like this for now, and I'm going to just try to blur it a little bit using this drawing program. So that's nice. Okay, so there it is. We have the electrons. Kind of a mess, but that's okay. And of course, because the protons are positive charge, then we have to have something assigned with the negative charge. And then the negative charges are attracted to the positive charges, and hence why the electrons, quote unquote, stay on the atom, because they are attracted to the protons. We're following very simple electrostatic rules. Just think magnets. If you have a positive charge, then that is attracted to a negative charge. Opposites do attract. And of course, if you have like charges, if there's a plus charge and then there's a plus charge, they will repulse each other. They're disgusted by each other, metaphorically. So this causes a repulsion. And similarly, if you have a negative charge next to a negative charge, they're also repelled. So we'll put repulsion. This plus plus is also repulsion if they get close together. And then of course, again, going back to the opposite charges, there will be an attraction. So alright, so that's going to be the fundamental rules that you will need to know for starting off about the atom. In terms of talking about the atoms, starting to talk about the atoms. So we have the hard part, which consists of the protons and the neutrons, and then around that one, aggregating around that would be the electron clouds that are attracted to the positive core. But of course, there is a kind of a fundamental hidden question when you look at the nucleus. The nucleus consists of pluses and neutrons, and then didn't we just say that there's repulsion between same charges? Right? If we have pluses in the middle in the nucleus and they're hanging out next to each other, well, shouldn't the nucleus come flying apart? And that's actually a pretty interesting question with a very funny answer. So, this is a thing that scientists explored. So they're like, as the scientists were looking at this, they're like, wait a minute, if there are pluses next to each other, they should be flying apart. So therefore, there must be some sort of force that's keeping them together, and it has to be very strong, otherwise these pluses will come flying apart. So that's what happened. So they decided to call this fundamental thing that's keeping these pluses together, they called it the strong force. Very, very creative name. So yes, so short answer is as to what keeps the nucleus, the core of the nucleus together, is the strong force, which seems like a no answer, but it's the answer for now. And the strong force pretty much is related, is basically part of the neutrons. So the neutrons help to keep the nucleus together. If you want to go into more detail, it's not going to be done here, definitely for sure. But again, just the short answer, the neutrons help keep the nucleus together, despite there being strong repulsive forces between the protons. The quote-unquote strong force keeps the nucleus protons together. Fun. Okay, but that's not what we're talking about today. We're just talking about atomic model basics, the modern atomic model basics. Okay. There's a lot more to talk about in the future. We're talking about orbitals, talking about MOs, molecular orbitals, but that's going to be saved for much later. But for now, you're just going to have to accept that the clouds of electrons are attracted to the positive neutral core. And as you go through your chemistry career, you may have learned that there were like early on in your chemistry career, like maybe middle school or so, you may have learned the Bohr model, where there's like a discrete center of the atom, and then you have those little circle orbiting patterns like this, like the planetary model. And then the electrons will be placed as like this in this particular fashion. There's like 2 here, and then the teacher will go on to put like maybe 7 right there, for example, or 8, and then they move on to the next one, and it feels like there's a bunch of little orbitals, little planets orbiting some sort of sun system. But this is called the Bohr model, and it's basically, it's useful for a visual representation, because human beings can't imagine things very well, so we need nice pictures, and this is a nice picture. But it is unfortunately, it is a model that doesn't have very accurate predictive powers. So as such, it's fallen out of favor a long time ago, but we still use it for visual representation. So this one is inaccurate in terms of many things, but particularly because of its inaccuracy in making good predictions. Okay, so that's the planetary model. Again, we're contrasting that with the modern atomic model, which talks about electrons as clouds aggregating around the nucleus in certain spheres, in certain locations around the nucleus. Okay, so that's this one. I'm gonna use it probably a little bit, but I'll try to generally preface whenever I draw. I'll preface it by saying it is an outdated. It's not a model that we really use. So yeah, we'll ignore that for now. Okay, so again, modern atomic model. And we're going to clear this. Yeah, delete. Okay, so when we talk about atoms and we talk about interactions, it's important to understand that when you learn it on the periodic table, it's all in a kind of a pure elemental form that exists in a reality where there are no other atoms. So what I mean by that is, when you learn about hydrogen, for example, if you look on the periodic table, it has a number of 1. So what that means is that has 1 proton. So there's 1 discrete plus particle in there. And then you might have like a neutron. What's the color? Okay, there's like a neutron there, and then that's going to be the nucleus, and then surrounding that would be a singular electron cloud density, which again we'll represent using a cloud or a smear, like that. So, but what you learn on the periodic table is just for reference purposes. It doesn't exist like that in real life, because atoms are next to other atoms, or atoms are floating around and colliding with other stuff in the environment. So as such, this is not the reality of the situation. It's just a useful reference point when you're doing chemistry problems. Okay, so I just want to get that out of the way. So let's get to a fake situation that's closer to reality somewhat. So if you have atom number 1, it has a nucleus right here, and then it has its electron cloud smear. Oh, that's a little too... Okay, there's an electron cloud smear, and then when you... And then we have atom number 2. And it also has this electron cloud smear. So when we talk about these situations, we're talking about atoms interacting with other atoms. So if atom number 1 is floating randomly like so, and then atom number 2 is floating randomly like so, and then they encounter each other, something very amazing happens. And the amazing thing that happens is they simply just drift apart. But why is that? Going back to fundamental magnetic rule number 1, if you have same charges repel same charges. What are electrons? Electrons are minus charges. So that cloud that's surrounding this nucleus is minus. And then the charge on this electron cloud is also minus. So when you have minus floating next to minus, they simply push each other apart. It's very boring. But we can make things happen if we really wanted to. So that's when these things are floating very slowly. So if you have atom number 1 just drifting randomly in Brownian motion across space and it's very slow, it simply gets repelled by another atom. But if you somehow manage to accelerate these particles that are floating around in space, these atoms that are floating around in space that miraculously have not interacted with anything else. So if you accelerate this one, what happens is that you have these cloud densities, and it's very important to emphasize that they are cloud densities. Electron cloud densities, they actually phase through each other. So it's kind of interesting. So again, you have atom number 1 that's moving very quickly, and then you have atom number 2 that's also moving very, very quickly. If they happen to smack into each other, is that they have this overlap, and this is a very interesting situation. So let's emphasize the form here. So you have this overlap of electron density, and it's very negative because again you're phasing one electron cloud, which we've already established that electrons have been arbitrarily assigned a negative charge, and then if you overlap it with some more electron cloud density, then that's also a negative charge. So this region right here is going to be super negative. There's a very high degree of negativity that's happening in that overlap between those two atoms. Now, a number of things can happen, but the two main ones that can happen is number 1, the atoms simply cannot stabilize this charge and they just come flying apart. So that's one thing that can happen. And then another thing that can happen is the overlap between those two electron densities can actually be very good. But, what does it mean to be very good? And then you have to talk about molecular orbitals, which let's not talk about that. Not today. So, long story short, there are certain types of forms, 3-dimensional forms, in which electrons can aggregate around, that you can probabilistically find electrons around an atom. And those things are called electron orbitals. So when I'm talking about overlap, we're talking about the overlap of 3-dimensional space. So when you have one orbital overlapping into another orbital, if the overlap shape is good, then this region of high negativity can actually be stabilized by the plus charges of the nucleus. So there it is. But if the overlap in those electron density regions are very poor, something like this, for example, later on you'll learn this is called like an anti-bonding orbital, but don't worry about that. For now, if the overlap is poor, then what ends up happening is these two atoms just simply separate and go on their own separate merry ways. So long story short, for this one, after the atoms have collided and overlapped their electron densities, if the overlap is good, then this highly negative region can actually be stabilized by the flanking nuclei number 1 and nuclei number 2. So this overlap is maintained, and there's a bit of energy release, and we have something formed called a covalent bond. So there it is, covalent bond. Nice. And some people will describe covalent bond as kind of a sharing, but I don't know. I personally never liked the word sharing for electrons when we're talking about atoms. But for now, when you think covalent bond, I encourage you to think about it as electron cloud densities overlapping and being stabilized between two nuclei. Okay? Okay, so basically overlap of electron densities. Some people call it sharing, so I'll put that in, I guess, quotes, sharing of electrons. But, you know, the word sharing sounds like a nice situation, like you're in kindergarten and then you want to share your toy with someone else, and it's very nice and everyone is having a good time. But in chemistry, I would say it's a lot more uh, self-serving, so to speak, rather than sharing, because sharing implies there's some sort of equality, there's some sort of nice equality going on, but that ain't happening in chemistry. In a lot of chemistry, you have like unequal stuff. You have atoms fighting over electrons from other atoms, stealing things, rather than having this nice sharing concept. So let's not put that after all. So the covalent bond is just simply going to be a stabilized overlap of electron densities. So I'll just call it overlap of electron densities. But also important to this idea of overlapping electron densities is the fact that it's stabilized by the geometries of the orbitals. So stabilized. And the stability is very important. So how do you know if it's stabilized? Well, for now, you won't know. Later. Okay. Wait a minute. Let me go to the board. Let's cut myself off from here. Let's just go straight to the... Okay, perfect. Yeah, there we go. Now, you can see what's going on. Okay. So again, just to go over quick, the summation, I guess, we have the covalent bond, which arises from collisions of atoms. When you have atom number 1, the electron cloud density phases through another electron cloud density of atom number 2, usually because they are moving very quickly. They have high velocities. And when that overlap is stabilized and sustained, then we call that one the covalent bond. All right. So that's not the only things that can happen between atoms, of course. So you can have atom number 2. You can have atom number 1, So there could be atom number 1, and then there could be atom number 2. And then you have electron cloud densities, of course. Electron cloud, electron cloud. What we can have is we can have atom number 1, and then it's going to be next to atom number 2. They get close enough, and what ends up happening is atom number 2 steals electrons fully from atom number 1. And why does this happen? Well, maybe we'll get into that today. But let me try to draw this picture appropriately. Hold on. Let me go back. Separate layers. We'll have to undo the layering. There. Yeah, there we go. Okay. So when we have atom number 1 next to atom number 2, sometimes, depending on what the atom players are, is what ends up happening is the cloud number 1 could get sucked by atom number 2. It does the sucky. So here we go. So this basically gets kind of drained into the other electron. Not all of it, of course. We'll talk more about that in detail. But there is a degree of electron transference. It's like a full electron assignment that's sucked over to atom number 2. Because atom number 2 is quote-unquote greedy for electrons, and when it happens, you get a full transfer of electrons. So let me symbolically represent that with this red arrow. So we have one electron cloud density that's going to be fully drawn into atom number 2. So there's a sort of a stealing going on with that situation. I'm going to keep this up, but to conceptually visualize it better, I'm going to draw another picture. This is a snapshot afterwards. So what ends up happening is you have atom number 1, which lost some electron cloud density, so it's a little smaller. And then you have around atom number 2, the electron cloud density is a little bigger because, again, it stole some electron. It stole at least one electron from atom number 1. Okay, and then of course we're going to do some basic mathematics. So this is if atom number 2 gained an electron, stole an electron from atom number 1, then we can represent that mathematically with a plus. So it's going to be plus gained 1 electron. And remember, electrons are assigned a negative charge arbitrarily sometime long ago. So when this atom number 2 gains an electron, it gets a plus with a minus 1. So it gains, it gains what this first plus means, an electron, which is what this minus means. So when you plus a minus in math, it's going to be negative 1. So symbolically, I'll represent it with this right there. So that is a negative 1 charge overall on this particular atom because it stole 1 full electron from atom number 1. And then atom number 1, because it lost an electron, we will represent that using a minus. And since it lost an electron, which are assigned a negative 1 charge, that's a minus 1. And, you know, double negatives from when you're doing your algebra 1 or pre-algebra days, that's going to be a plus 1 charge. So that's overall charge is plus 1, which we again will denote, we'll represent using this symbol with a plus, blue plus. Okay. And then something very interesting happens between those two. Following our established rules of magnetism, if you have opposite charges, they will do an attraction. So positive charge here is fully attracted to a negative charge right there. So when that charge happens, you get a bond formation. And this bond formation is distinct from the previous one we talked about, which is the covalent bond. So this is not a covalent bond. This is strictly a bond that forms because of this full negative being attracted to this full positive. And again, that full negative arose because this atom number 2 was greedy for electrons and it had proper spacing and it stole electrons from atom number 1. So again, when you have that opposite attraction, they stick together, and thus you have something called the ionic bond, which I will write here. Ionic bond, there it is. Nice. Again, contrast that with the covalent one, which has to do with overlapping of electron densities, and then the overlapping is between and stabilized by the flanking nuclei. But this one is just attracting because of the exposure of one atom is slightly more naked now, so to speak, and thus it's going to be a positive charge, and then that positive charge nucleus is actually attracted by the electron cloud here is attracted to the exposed nucleus right there, slightly more exposed than what it was before. So opposites do attract, and that's the ionic bond. All right. So that's going to be another bond that we talk about when we talk about atom bond formation. Again, the first one's covalent, this one is ionic, and then we'll get to the third one, which we'll talk right now. So when you have atom number 1 and then you have atom number 2, again, same old story, begins the same way. When one atom loves another atom and it has the electron cloud density right here, and then this one also has electron cloud density, once they get close to each other, some interesting interactions could potentially happen. So in this case, the electron cloud density actually drifts over to the other one, and vice versa. The electron cloud density from atom number 2 also drifts over to atom number 1, because for these particular atoms, the electrons are kind of loosely held. We'll talk about why they might be loosely held later. But for now, just know that they are loosely held, and because these electrons are loosely held, they can drift freely from one nucleus core to the other, surrounding the other nucleus of the other atom. Because again, the electrons are kind of transient, they're very loosely held, they're delocalized, so they can flow freely from one to another. So in fact, if you decide to put another nucleus, another atom, right here of the same type, that one also comes with its electron cloud density. What ends up happening is the electron cloud densities are shared, or the electron cloud densities flow freely from each atom onto any of these other atoms. So there's a high degree of traveling for these electrons. So that one is very interesting. And this is what we refer to as the metallic bonding. So that one is from when the electron cloud density are spread over a multitude of nuclei. Again, contrast that with the previous two. For the covalent bond, that arises from overlap of electron cloud density, stabilized by flanking nuclei. Covalent ionic bonds are when one atom fully steals an electron from another atom, and then because there are resulting full positive and full negative charges, they stick together, and that forms the ionic bonds. And then last, this one that we're currently staring at, that's referred to as the metallic bond, when the electron clouds are free to shift from one atom to another atom and to another atom, because the electron cloud is so loosely held by its original atom nucleus. So it's free to drift elsewhere. That's the metallic bond. So we have three bonds by which we will talk about for chemistry, general chemistry class. So let's put them all together side by side. So it looks nice. So we'll just partition these off. Again, we have the covalent. We have the ionic. We have the metallic. Whoops. So again, nucleus number 1, nucleus number 2, and then you have electron cloud density that is quote-unquote kind of shared between them to a certain degree. You have electron cloud overlap, and that's stabilized by flanking nuclei. For the ionic situation, that is when you have a full transfer, full stealing of electrons from one atom to another atom. So this one is a full negative, for example, and this one has a little bit. That one's like a full positive charge assignment from if you just do the math. So it's full positive. This is a full negative. And then because you have these resulting charges, opposites attract. And then they stick together, and we refer to that as the ionic bond. Let me not try to cut off the picture. Okay, there we go. Okay, there it is. And then lastly, we have the metallic bond, which has the delocalized electrons, where electrons are free to travel between multiple nuclei. So let me put 5 nuclei down. So you have electron clouds drifting from here to there, from this bottom one to this one, maybe to this one. And then this one drifts over to here, and then the electron clouds are all over the place, and that's how you hold all these atom nuclei together, is when you have this overall super sea of electron cloud density that holds them all together. And you get connected atoms as such. Okay, and of course there are a few important rules to go over. If anything, you can just memorize these rules and it will help carry you a bit of the ways, but definitely try to internalize some of this electron cloud density idea, because I think at least, it will definitely help make your life easier if you ever plan to go into farther chemistry, like organic chemistry, or even just you just want to understand things and not simply memorize, then electron cloud model is very useful. Okay, but here are the rules, fundamental rules. Of course, covalent, this atom number 1 that we talked about is referred to as a non-metal, which I'll explain, of course, but let me write this down first. This is a non-metal. And non-metals are going to be greedy atoms, and then this is going to be non-metal number 2. I keep putting non-metal, whoops, non-metal. So that's non-metal number 2, and then here you actually have a metal. Actually, I should use blue. Okay, this is going to be a metal. And then this is going to be a non-metal. Again, non-metals are going to be greedy. If you want to follow rules, that's the rule to follow. Non-metals tend to be greedy, and then metals tend to be less greedy. And then when we talk about the metallic bonds, those ones arise when you have multiple players that are all metals. So for sake of easier discussions, these ones are all the same metal types. So there aren't any differences in greed. So this is a metal. So you won't have one metal, for example, hogging electrons more than other metals, which is kind of the basis for electrochemistry. So we'll keep it simpler, I mean. So all the same metals. So when you have nuclei that are sharing electrons with each other, there's a good joke about this one in terms of communism elements. So this one will be, one of them is, I wouldn't call this one the sharing one really. This is when one atom is basically, two atoms are basically fighting over electrons because they're greedy for electrons. They have nuclei that are positives, and those nuclei will attempt to pull negative cloud densities to themselves. So this is going to be fighting here, but then of course the cloud overlap is stabilized. And then here you have a full stealing. But here is where you get the sharing, the whole communism idea. Like, this is our electron cloud density. This is still the fight is on. This one, the fight is over, and then this one, there is no fighting, kind of, as the electron cloud just drifts over all the atoms. So it's our electrons. Alright, that's the four, the 3 main types of bonds when we talk about chemistry bonds. So here we go, bonds. Bond number 1, bond number 2, and then bond type number 3. Again, non-metal to non-metal is covalent. Metal to non-metal, it would be ionic. Full stealing of electrons, and then you have metal to metal. That's basically electron, referred to as the electron C model. But you know, got to dive a little bit deeper into why there are some atoms that are quote unquote greedier than other atoms. All right, let's go to a crudely drawn periodic table right here. Something like this, right? I hope that's right. Okay, and then like for example, this is where you find hydrogen, and then this is where you find helium. So when you learn the periodic table, you'll learn that the periodic table is organized in a very useful way, because you can get multiple lines of information just by looking at the periodic table. And I guess to start us off, one of the useful things you can get is something called the layers, the energy levels of your given atom. So going to the Bohr model, which is again inaccurate and outdated and no longer really in use, but you know, still nice visually. You have the nucleus, and then you have electrons around it. So when we look at the periodic table, this is organized in a very useful way. This one is called row 1, period 1, and then this one is called period 2, and this one's called period 3. So when we talk about periods, we're talking about something called layers for your electrons, because your electrons gather up around your nucleus in very specific ways. But the simplistic way of thinking about this is just a singular layer, but that's not correct. But for now, we'll accept it. So if you are in row number 1, this is period 1, then we have one energy level, one layer to first think about. So when you go to the Bohr model, that's going to be the first circle around this nucleus. So again, this is the nucleus, this is the positive neutral core, and then this one is a discrete particle of electrons. Remember, it's not supposed to be like that. So that's the first row of the periodic table. So when you go across, all you're doing is you're going to add one more electron to the current layer. So this one, again, hydrogen is in row 1. So it has one energy, it has one layer, and because you are in space 1, then it's going to have one discrete particle in this drawing. But when you go to helium, you are still in row 1. So helium is going to have one layer, but because you are space number 1, space number 2, you're going to assign it 2 electrons. Okay, 2 electrons, because 2 electrons can be attracted by 2 protons. There it is. Why does it have 2 protons? Well, because by definition, if you look at the number, it's called the atomic number for helium, you will notice that the number is 2. And that just simply means that's how many protons are at the core. That is how you identify. That is how we name something as a helium. Like, what is a helium? If a given atom that you're looking at has 2 protons, then by definition, by our human definition, it is a helium. If it has 3 protons in there, then by definition it is not helium, because it has 3 protons. It would be this one right here, which I think is lithium. Lithium has 3 protons by definition. That's the only criterion by which you would use to define what element you're looking at. It's not the number of electrons, it is not the number of neutrons, it is strictly the number of protons, because electron numbers can change, neutron numbers can change, but the only thing that we keep consistent, that we like to frame as consistent, will be the proton count. Okay? But I guess this discussion is kind of messy, because I didn't pre-plan this lesson, but that's okay. I just picked a topic and ran with it. But again, just to emphasize again, this is row 1, period 1. You know, like when you read an English sentence, you read from left to right. So as you're reading it, you read to the end of the sentence, and there's a period. So that's the end of the period of the sentence. So in a likewise fashion, you read from left to right, and each space you move, you're talking about a different element, because we're talking about one more proton as we move from left to right in a singular fashion. Okay. I wish I could delete these. Yeah, there you go. So that is for the first row of the periodic table, the first period. Of course, once you get to row number 2, that's going to be energy level 2, but don't let that sound too fancy. It just simply means you are in the second energy level, which is the second layer if you're looking at the Bohr model. And in this second layer, all you have to do is just add more protons to it, because these spacings can be filled up with electrons. Which brings us to something we hit a little earlier right there. The fundamental rule is, again, if you have a single proton, you can attract a single electron, which is a cloud, not a discrete particle like this. But keep it simple. 1 plus can attract 1 negative. So if you put 2 pluses, then you can theoretically attract very very well 2 electrons. So it's like a one-to-one trade-off, right? For the most part. So again, if you add one more plus here, you can theoretically attract one full negative, which is a cloud. Okay? So when we go to lithium, which is Li, once you reach the lithium, that one basically is atomic number 3. And again, what that means is you have 3 protons. So it's 1, 2, and then 3. So you can theoretically attract 3 electrons, which we denote this Bohr model is this is 1 electron, this is 2 second electron. But because again lithium is in row 2, it has 2 layers from which you can put electrons. So we put the electron right here on the Bohr model. But you might be asking, well, wait a minute, why can't we just put it in the first row, in the first layer right there? And the answer is because there's no space. Simply put, no space. Why is there no space? Because there are already 2 electrons right there, which sounds kind of like a tautological argument. It's not enough because there's not enough space. But putting it more simply, electrons are clouds, remember? And when you have clouds concentrated in a small amount of space, they actually push each other apart. It actually causes repulsion. So if you have 1 electron right here and then you have another electron right there, that's 2 electrons, then if you put them in a close spacing, they actually push each other apart. But because there are 3 protons right there, 3 protons is enough to attract those clouds, those 2 electrons close together. But the third one simply cannot occupy the same space because 3 protons are not enough for that one. And the 2 electron clouds will repel the third electron cloud that's trying to get in. So the third electron cloud doesn't go in. So as a result, it's relegated to being outside the internal sphere, so to speak. I hope that makes sense. But if that doesn't make sense, it's because like charges repel like charges. And it just seems empirically that 2 electrons are the limit to what you can put close to the nucleus. Any more than that, the electrons just simply repel each other because this innermost layer is very small, and when you try to put a bunch of negative charges together in a small amount of space, they simply push each other away. So 2 seems to be the limit from what we've observed across all atoms. I hope that's specific enough. Okay, but again, going back to the main discussion, energy level number 2. So we are talking second energy level, so that is where you put the third electron. Why is it third electron? Because again, lithium has 3 protons. It can theoretically attract 3 electrons on a one-to-one basis, but the third electron cannot occupy the same general layer as the first 2 because it's too tight of a space, so it gets pushed out. But it doesn't get repelled away because it's still somewhat attracted to the positive neutral core, even though it's surrounded by those 2 electrons. So that's nice. It's still attracted. Okay, so that's energy level 2, and of course the discussion just extends farther. So if you're looking at energy level 5, for example, then you're going to row 5. So this is again row 1, row 2, row 3, row 4, row 5. So if we're talking about energy level 5, you basically can represent that on the Bohr model with 5 distinct layers. So you have the positive neutral core, you have energy level 1, that's like again the first row, those ones are occupied with electrons. And then you have energy level 2, which is also occupied with electrons. It happens to be 8 for the second layer, and then when you get to the third energy level, that one's also occupied by electrons. And then you get to the 4th energy level, and then you get to the 5th energy level. So we're talking about the 5th. I'm running out of space. So that's the 5th layer. using the Bohr model, which is, again, just to emphasize, it is a model that is not very accurate for predictive powers. Okay, but what's happening in the fifth? Well, again, there are a bunch of electrons in the inner layers. Because there are electrons in the inner layers, any new electrons that you're kind of putting onto the model, they get pushed out to the farther layers because electrons inside push away electrons that are trying to come in as you try to put them on. In a way. So again, this is the Bohr model. There's something called the octet rule. I won't really cover that because octet rule, honestly, is only really good for like these energy level 2. It's called the octet rule, rule of 8, and it only really applies to these atoms right here. Once you go farther, the rule kind of not super useful. It's a good starting point, but not that useful. Only for here. Okay. So again, electrons tend to aggregate around in layers around the atom, and as you go down the periodic table, then the electrons you are quote unquote placing onto your atom in your model get farther out in terms of the layers. And this leads to a very important idea. And it has to do with attractive powers. But let's clear the board. So in terms of what's happening is if you have an atom here with a nucleus, let's say we have 1, 2, 3, 4, 5 electrons, right? We have 5 electrons right here, and then you have 6 electrons. I mean, did I say electrons? I mean protons. We have 5 protons here, and then we have 6 protons right there. So 5 protons versus 6 protons. And this is in the magical world, okay? So at the moment, these ones don't have electrons around them. This is just strictly 5 protons somehow staying close together. And this is 6 protons, again, somehow staying close together. This is not the real world. This is just a thought situation. So if I put 1 electron right here, which again I'll represent using a singular cloud, and if this cloud was passing exactly like this between them, the question is, to which direction will this electron be attracted? More strongly attracted? Will it be more strongly attracted to this 5, or will it be more strongly attracted to this 6? And the answer here is, of course, very simple, because this is not the real world, and there are no other electrons. Because there are no other electrons, aside from this one question, this electron will be more strongly attracted to the 6 protons, simply because of the sheer amount of 6 positives beats 5 positives. So this one is more effectively attracted to this one. So, very simple idea. So if you have 1, 2, 3, 4, there's going to be too many to draw. So if you have 20 here, for example, and then you have 13 there, for example, and then we move this electron that's drifting between those two to which group, which conglomerate of protons will this floating electron be attracted to? Will it be attracted more strongly to this 20 or more strongly attracted to this 13? Again, these are naked protons. They are only protons. No electrons. Neutrons, we don't care. But right now, there are no electrons here. Neither are there any electrons over there. So given this scenario, this is more strongly attracted to 20. Of course, by the same rule for here. It's simply a numbers game. If you have more protons, then you have more effective attraction for electrons. Very simple rule. Alright, so if we get to something like carbon and oxygen, let's look at what happens with those in that particular scenario. So if you have carbon, which if you check on the periodic table, I think it was 12. And then if you check the periodic table for oxygen, I think it's a... Wait, before I make a fool of myself, let me look it up because I don't remember their atomic numbers anymore. So give me a moment. Periodic table. Let me just search it up on my search engine. Unsponsored search engine. Unspecified. Unsponsored. Oh my goodness. It's not 12. I'm sorry. That's 6 plus 6, which would be 12. It's only 6. So 6 protons there. And then if you check the oxygens, it is only 8 for the atomic number. But remember again, atomic number is strictly the number of protons, which, you know, the number of protons is the definition, is the criterion we use to determine the identity of the element on the periodic table. So we have carbon, which has 6 protons, and then we have oxygen, which has 8 protons. And now this is closer to the real world because this 6 protons is with 6 neutrons typically, and then these 8 protons are next to typically 8 neutrons. So 6, 6, and 8, and 8. Okay? And then they also have electron cloud densities around the atoms. So if you check the periodic table, which is not real life, you know, for the most part. So oxygen will have 8 electron clouds organized in discrete layers, and then carbon will have 6 electrons organized in certain layers around that one. So now we're gonna have 1 electron floating right here, and we're gonna send it on its merry way strictly between those two in a very perpendicular fashion. And then the question, of course, becomes to which atom will this electron cloud density be more strongly attracted to? Will it be attracted more to this oxygen, or will it be more strongly attracted to this carbon? If you just look at the numbers game, it is an 8 proton count versus a 6 proton count. So just by looking at the protons, we can say that this electron cloud density is more strongly attracted to 8 protons, all else being equal. Okay, that's very important, all else being equal, but as usual, more on that later. So yes, this electron cloud density is more strongly attracted to the oxygen. Yes, I'll just put yes. All right, simple enough, right? Okay, but of course, you know, that leads up to the setup. If I said that was simple enough, then why am I saying that, right? So if you have something like oxygen, going back to oxygen again, which is again has, what was the number? 8. So let's say we have oxygen again. On probably 8 neutrons, and then it has for sure 8 protons, probably 8 electrons. And now we will have oxygen duking it out with something like potassium. Or, yeah, let's do potassium. So potassium, if you check the periodic table, it's in row energy level 5, row 4, column 1, so K. KO. So we have potassium, which begins with K, not P, for historic reasons, because of whatever language it started with. Potassium was not named potassium. I think it was named with something beginning with K, but for some reason it changed to potassium, but the letter did not change from K to P, which would have been nice, but then we get confused with phosphorus or something. So we kept the K, even though that's not what potassium doesn't even have a letter K in it. But again, it was like it might have been Latin or Greek. where the original name for potassium began with a K. Alright, but that's not important. So potassium, if you check the atomic number, is 19, which again, the atomic number is strictly the number of protons. For potassium, the number of neutrons, I don't remember what it is. It's actually not, I don't think it's 19, but let's just say it's 19. So I'm going to put, in quotations, 19 neutrons, which is not part of a discussion, but I'll put it down. And it probably has 19 electrons. Okay? And of course, we're going to have the electron cloud right here, a singular electron cloud, and of course the question is going to be the same as before. If this electron cloud is magically drifting between those two, to which atom will it be more strongly attracted to? Would it be to the oxygen, which has 8 protons, or will it be to the potassium, which has 19 protons? And you know, remember the setup for this particular situation. I said sounds simple enough, right? So this is probably some sort of trap question. So if you look at strictly the proton count, one might be tempted to say this electron will be more strongly attracted to the potassium. And of course, if you suspect it's wrong, that is the wrong answer. But you know, you're like, well, hey, wait a minute, what gives? Like, shouldn't 19 proton, shouldn't that beat out the 8 proton? Since by raw numbers this is more than twice. And yes, 19 proton actually is more strongly attractive to grab electrons than our 8 protons. But that's if protons are the only things you are looking at. But it's not just 19 protons, it's also 19 electrons all surrounding those 19 protons to begin with. And the same is true for the oxygen. Those 8 protons are surrounded by 8 electrons. But remember, the electrons aggregate around the atoms in layers in very specific patterns depending on which orbital you're looking at. But we'll do a simplistic drawing. So check the periodic table again, reference the periodic table to get an idea of what's happening. If you look at oxygen, it is in row 2. So if we draw the Bohr model, which is again wrong, it has 2 layers. Actually, all models are wrong, but that's fine. So oxygen has layer number 1, and then because it is in row 2, it has energy level 2. So because oxygen has 8 electrons, we can symbolically represent 2 on the inside, because again, the inside is very close to the nucleus, it's very small, as such it can't hold that many electrons, and 2 seems to be the limit. So 2 electrons aggregate around there, and then you have the remaining 6 electrons which aggregate in the second layer shell, which holds up to 8. But right now, we don't have 8, we have 6 for the second layer for oxygen. So that's what we're going to represent oxygen with this particular picture. And then if you look at potassium, potassium is going to be row 4, energy level 4. So thus, we can represent it using 4 layers. So here's the nucleus, here's 1, very close. Here's second energy level, that's 2. This is the third energy level, 3. And then because potassium is in 4th row, you can have 4 layers for this drawing representation. So 19, we have 2 in the first layer because it's close and very small. And then we have, again, we're going to have 8 for this second layer because that seems to be the limit octet rule, 2, 4, 6, 8, and then for the third level, because again potassium has 19 electrons, we currently have 10 on the board. So third layer, we're going to put more electrons here as discrete particles for the Bohr model. So that's going to be currently 8 plus 8 plus 2, which is 18. So we have 1 more electron to place. I'm going to arbitrarily place it right there. So we have the 2 visual representations via the Bohr model. We have potassium right here, which is huge. I should draw it, not to scale, but you know, it's clearly just by this visual crude representation, it's already bigger than oxygen. So that's potassium, and then you have oxygen right here. So going back to the main discussion, why is the electron cloud density not more strongly attracted to potassium, which has 19? So in fact, I should have drawn this a lot bigger, because more protons should have a stronger attractive power, and it does in a vacuum without any other electrons. But here's the thing though, because this electron is drifting, remember electrons are negative charge assignments. In order for this electron to be attracted more strongly to this one, alright, let me rephrase that. Basically, for this one, this electron is attracted to this nucleus to a certain degree, but how much is that degree? So in order for this one, as what's attracting this electron is this nucleus, right? But the thing is, for this potassium, there are already a lot of electrons residing on this potassium, and they're residing in a way such that this one is actually very poorly attracted to the core. And one of the simplest answers to explain why is because there are just too many layers of electrons. Okay, so despite there being a treasure trove of protons hanging out in the nucleus, 19 of them in fact, they are actually surrounded by just too many electrons. So there's electrons here in that layer, electrons in that second layer, electrons in that third layer, and then that singular electron in the fourth layer. So as such, this electron has a very hard time being attracted to this core, simply because there are so many layers of electrons. So this is a phenomenon referred to as electron shielding. You can just call it electron repulsion, honestly, because electrons, again, are minus, and this is also a minus, and this one has a very hard time being attracted to the core nucleus because it's surrounded by so many negative electron cloud densities. So this one doesn't experience a very strong attraction, relatively speaking, to something like this. It's all relative. You typically never talk about atoms in a vacuum. You're always talking about atoms relative to other atoms. So when I say potassium is weak, it's basically in this context in comparison to something like oxygen. But why is oxygen so much better? So for attracting this singular electron, because oxygen, despite having only 8 protons, it's surrounded by much fewer electron cloud densities. Only 2 layers, in fact. So this 2 layer makes a very big difference in comparison to 3 layers. And you can't really tell it from this visual representation, because electron shells expand, layers of electrons expand not linearly. They expand by like magnitudes, like very big expansions. When you jump from one energy level to another one, you actually get like a much expanded space. So mathematically, just by using the discrete numbers, this is 2 layers versus 4 layers. You know, don't be tricked into thinking, oh, it's going to be 4 minus 2. 2 layers more than 2. It's not that much. It actually is a huge difference in terms of the spacing between electrons and their ability to be attracted to the nucleus. So I'm saying that again because this electron cloud density has a very difficult time being attracted to this nucleus, because this nucleus is just overcrowded with all those electron cloud densities. And then this one, despite there being 2 layers and only 8 electrons, because it only has, 8 protons, because it only has 2 layers, this one is much more strongly attracted to this one. Now I'm going to go to my favorite analogy to use when I'm discussing this type of stuff, and it's basically the taco truck analogy. So when I talk about the taco truck analogy, just imagine this, okay? You're it's gonna be lunchtime and you're getting out of class and you're with your friend, okay? So your friend goes, "Hey, I want to go. Let's go get some lunch." And then you're like, "Yeah," because you know you've just been sitting through your class, getting hungry because your brain has been consuming all those glucose, and you need that glucose in your brains. Otherwise, you can't think very well. So you agree with your friend, like you agree with your friend's proposal, like, "Yeah, sure, let's go get some lunch." And then your friend's like, "Let's get some tacos because it's Tuesday, Taco Tuesday, right?" And then you're like, "Yeah, sounds good to me." And then so you open up your web browser on your phone and you're like, "Okay, what do you want to get?" And your friend's like, "Hey, let's go get this place." And then you look up on your favorite food app, Help, Felp, food food help. Yeah, that's what it's called. You check your favorite app called Felp, and you look at the taco truck. There's taco truck number 1. You're like, "Hey, this taco truck looks really good, and it's like very close to school." And according to the Phelps, it has 4.7 stars or something like that. 4.7 stars, and then you make sure you check the quantity as well, because you know if it's just 2 reviews, that's kind of suspicious. But you check the review, you check the number of reviews. It's a whopping 2,345. Wait, that's too weird. That's too suspicious. It's 2,700 and it's 2,371 reviews on Felp, and it's 4.7 stars. So that's looking really good for taco truck number 1. And then you're like, "Okay, sure, let's go get that." So you go to the taco truck, and lo and behold, many other people had the same idea. So unfortunately, there's a huge line. So and that line is like wrapping around the taco truck for some reason, okay? So it's just a huge line that's wrapped. So there are those 4.57 star tacos in that taco truck. You are standing here, and your friend is standing there, and you're both looking at the truck. You can't even see what's going on because it's just surrounded by this huge line of people that's wrapped around the truck. So you look at your friend, and you're like, "You know what? Forget it. Maybe this is not a good idea." But your friend goes, "No, I really want those tacos because, you know, it's Taco Tuesday." It's like those $1.25 tacos because of inflation nowadays. Not $1 anymore. It's $1.25. So your friend's like, "Wait. Let's check Felp again." So you check Felp again, and there's another taco truck, but it's only 4.5 stars. You're like, "Oh no, it's only 4.5 stars." And then you look at the quantity of reviews, and it's only 385 reviews, and you're like, "Wait a minute, good enough for me." And then your friend says, "Okay, yeah, that's good enough. Let's go check the truck." So the truck, you go to the truck, it only has that much of a line. So you and your friend's like, "Okay, you know what? Let's go there. It doesn't look so bad." So you and your friend were repulsed by this taco truck number 1 because despite the tacos being of a quote-unquote higher quality because it's 4.7 stars, despite that, you are simply repulsed by having to wait in this excessively long line. Because look how long that line is. It's not worth it. No tacos in the world is worth waiting an excessive amount of time. And by the time you get there, your lunch is already over. So you know you don't even get to you don't even get to eat your tacos. So this is a no-go taco truck, simply because you're repulsed by having to wait there. But this one, even though the tacos are less, quote unquote, less attractive because it's only 4.5 stars, you know, let's make it a little more exaggerated. It's only 4.4 stars. So even though it's only 4.4, you're more strongly attracted to this one because it's more accessible. There's less occupation. It's less surrounded by other people. So you feel like you have a higher chance of getting in. So as such, you and your friend pick this taco truck. So yes. So what am I trying to say with this analogy? Basically, when you're talking about attractive strength of a particular atom, a particular atom's ability to attract electrons, it's basically an interplay between 2 major factors. And those two major factors are, again, pure proton count. That's pretty straightforward. Again, if you add one more proton, then you can attract, theoretically, one more electron. 1-for-1 trade, that's easy enough. So when the proton count goes up, then your atom strength, your atom's ability to attract more electrons also increases. But you also have layer numbers, number of electron layers. So how do we energy layers of electrons, let's say. Instead of writing electrons fully, I'm just going to put E with a minus. So when the number of electron layer goes up, it's harder for things to be attracted to the positive neutral core, because that positive neutral core is surrounded by so many layers of negativity. So electrons have a difficult time coming in. So the attractive strength for an atom typically goes down with increasing amount of layers. Okay? So this is an atom's ability to attract electrons. But that's kind of a huge thing to write. So instead of writing this atom's ability to attract electrons, we're going to simply write electronegativity. Concise, but it is jargon, unfortunately. Electronegativity. Now, you know, it's a nice clean word to put. Electro has to do with like electrons, and negativity has to do with negativeness of the electrons, which, you know, the name breakdown isn't that useful. But again, it's just an atom's ability to attract electrons when you consider the fact that it does have protons and it does have electrons. As a tangential item, there's also something called effective nuclear force, which, if you're taking AP chemistry, it might be relevant. So let me write this down. Effective nuclear force, which is, we need to contrast that with electronegativity. So effective nuclear force is when you totally disregard other electrons that are present on the atom. So this one, you're only considering the nucleus, which is the beginning of our discussion. Only the nucleus, and then again the electronegativity considers both the proton count and the layers of electrons, and this one, effective nuclear force, does not. So if you're thinking about effective nuclear force, it's only with the pluses. So if you have 28 versus 10, then 28 protons has a higher effective nuclear force than 10 protons. But if you have 28 protons, it doesn't necessarily mean it has a realistically attractive force for electrons that's higher than an atom that has only 10 protons, because you have to consider the layers of electrons. But this one comes more into play when you're talking about isoelectric atoms. Probably not today. Yeah. Okay. So there's that. I wish there was some sort of feedback, but I can't see what's going on. I have a feeling that what I'm discussing is kind of scatterbrained, but I felt like I had to do the stream today, otherwise I'll never stream again. So you'll have to pardon the disorganized fashion by which I'm proceeding through this discussion, this topic of atomic models. If I had to, I'll probably rename the stream, probably. But anyway, let's go back to covalent bonds, which is going to be the most relevant for biology people, but this is still useful for chemistry people, and it will be more useful in later sections like organic chemistry or electrostatic interactions, intermolecular forces. Definitely big play. You have to understand this if you don't want to memorize things. Oh, you don't want to memorize everything. it'll just be an overall easier time, in my opinion. Alright, so going back. This is in relation to covalent bonds, because that's not my favorite necessarily, but I think the most interesting to talk about. More interesting than metallic, more interesting than ionics. So we're talking about covalent bonds specifically. So it's been, we talked about this in the beginning, but I'm going to repeat myself because repetition is maybe the key to remembering things, or maybe not. So we have electron cloud density number 1, and then we have electron cloud density number 2. When those two cloud densities phase into each other, they can potentially be stabilized. So we have this huge overlap region of highly negative negativity. If the overlap is good, then the bond can be stabilized as energy is released. And again, we call this one the covalent bond. Just to be as precise as possible, I guess. It's this one right there. In a way, it's sort of sharing, but now we're getting to the reason why I don't like that word when we're talking about covalent bonds. So here it is. We just talked about atoms. We just talked about effective nuclear forces. We just talked about electronegativities, because depending on which atom you're talking about, each atom has its distinct ability to attract electrons, and some attract electrons better than other atoms. That's just simply the way it is. And here is the shortcut. If you look on the periodic table, fluorine is the greediest, the highest electronegativity atom on the periodic table. So fluorine right here. If there's one thing you should memorize, you should memorize this one. Fluorine, most electronegative. Again, electronegative, that's considering both the raw proton count and the electron layers. Most electronegative. So please remember that. F, fluorine, because fluorine is a mother effing greedy atom. It's super, super greedy. Again, if you compare it to something like hydrogen, for example, hydrogen, if you covalently bond those, you know what, let's not do that just yet. So just remember this. Key thing to remember. Fluorine is the most mother effing electronegative atom. Okay, F for mother effing, okay? If you want to memorize mnemonics, please reuse that one if you can. Don't say it in front of your teacher. Maybe, unless they're cool. Alright. Let's talk about the easiest thing to talk about. When you have hydrogen that is covalently bonded with another hydrogen. So again, that's atom hydrogen number 1. This is atom hydrogen number 2. They've already phased through each other, and that overlap of electron cloud density is stabilized because of good overlap. And then boom, you get this representation that's called a covalent bond. So because hydrogen number 1 is the same as hydrogen number 2, because they have the same proton count, then their ability to attract electrons should be equal. So when you have this electron cloud density tug of war between hydrogen number 1 and hydrogen number 2, neither will be the winner because they are equal players. And when you have equal players, there is no victory at overall times, okay? So there's a very specific word. There are multiple words to describe this, but here is one of them. This is called a non-polar situation. But I'll explain this word more when I introduce polar. So, but the short thing is, hydrogen, when it's covalently bonded with another hydrogen, it's an equal distribution of electron cloud density on average. So as such, we call that a non-polar bond. Nice, very nice. So in this case, if you want to describe this one as sharing is sharing electrons, then this would be the perfect time to do it, because that is when the electrons are shared. Okay, but again, sharing makes it sound like a very nice situation, but it's oftentimes more of a battle, more of a struggle, an epic struggle over electrons, or tossing of electrons. So that is an equal, quote unquote, sharing of electrons. So we're going to contrast this situation with something that's very easy to contrast with. So if we're talking about hydrogen number 1, and then we're talking about fluorine right there, remember what we just said, remember what we've just established. Fluorine is the greediest mother effing atom on the periodic table. Why is that? It's because it has a perfect compromise. It has a perfect ratio of electron layers and proton count. Okay, it's like the perfect compromise. It's like you found the perfect taco truck where the tacos are so good, but at the same time, the line that wraps around it is not that bad. So you are willing to wait for these good ones. You will definitely go to this one over any other one, despite there being better tacos, despite there being less of a line. This one just happens to have the perfect ratio between electron layers and proton count. Okay, but again, we've already phased electron cloud number 1 through electron cloud number 2, and then the overlap of this electron density has already been stabilized. But now we have to talk about the electron tug of war. So what's happening between those two in this covalent bond? So again, in this situation, fluorine is a super greedy atom. Hydrogen is weakly greedy. It is kind of greedy, but remember, everything is always relative fashion. So in comparison to fluorine, hydrogen is not that greedy. So as such, the fluorine will suck up more of the electron cloud density to itself, simply because two reasons. Because number 1, it has a higher electronegativity, and number 2, kind of neglected in some discussions, is it has a good amount of space available to accommodate that negative, the additional negative cloud that's pulling away from hydrogen. Okay, it is not a full transfer of electrons. You have to contrast, keep the idea of ionics separate from this one for now. So you have an electron density that's shifted more to the fluorine because fluorine is greedier. We're going to represent that using this particular arrow. So electron cloud shifts more over to fluorine. So fluorine has more electrons than it normally does on the periodic table. Everything on the periodic table is neutral, which is not real life, but it's just a starting point for doing problems. So fluorine, which naturally starts as neutral on the periodic table, as you go through the math, it actually gains electron density, but it doesn't gain a full negative charge. That is for ionic situations when you have a greedy nonmetal stealing electrons from a not very greedy metal. Then you get a full negative plus a full negative. But because this is not a hydrogen ain't going to give up its electrons. It still holds on to a little bit, but not all of it. So we cannot, again, we cannot give a full plus negative 1. So instead of doing that, we actually give it a partial negative sign. So it's plus this incomplete looking 8. Okay? So it's like an 8, but it is an incomplete 8, which represents partialness. So this is partial. So the fluorine gains a partial negative charge, represented using the incomplete 8 with a negative in front of it. Again, this is not ionic, so it is not a full negative gain. Alright, but let's cross this out because it looks ugly. Let's just clear some of the clutter. There it is. I mean, not there it is. There it's gone. So next to this end of the hydrofluoric molecule, I'm going to write a partial negative. And this hydrogen, because it lost a little bit of its cloud density, it gained its lost some partial negative, so it's actually partially positive. So this partial positive means that this nucleus core is slightly more exposed than if you compare it to the one on the periodic table, because the one on the periodic table has a full electron around it. This one only has less than full electron around it. How much less? Well, you have to look at the numbers. There's going to be an electronegativity table of values for a periodic table, but we're not going to fuss over that because that's more than what we need for right now. So just focus on the partial positive aspect of this hydrogen because it's slightly more naked than what it was before, because this fluorine is just so darn greedy. Alright, and something very funny, well not funny, but something interesting happens. Again, another interesting thing, because, you know, chemistry is just so interesting. You have this characteristic right here, and you know, you have one end which is partial positive, and then you have another end of the molecule which is partial negative, and this actually looks kind of like a bar magnet, does it not? Like when you think about it, there's like a north pole to this magnet, and there's like a south pole. Don't those have two distinct ends to it? There's a northern end and there's a southern end, right? And we can call this situation that arises, we can call this the dipole situation. Dipole. Di for two, right? Di for two, and then pole is, you've actually seen this before when you talk about the Earth. So let's go to the Earth real quick. It'll be the green representation right here. So when we talk about the planet, we talk about, there are distinct ends to the planet, right? There's like the North Pole for the planet, and then there's like the South Pole for the planet. So North Pole, currently the North is up, and then the South is currently down. Who knows when it's going to flip? Sometime in the future, maybe. Probably, according to the track record of the Earth, it will flip. But for now, North is on quote-unquote the top, and South is quote-unquote on the bottom. So this is North Pole, and then this is South Pole. And this particular Earth pole has two distinct ends. So this is describing like the overall magnet of the Earth, right? So you have this whole magnetic field about the Earth. But the important thing I want to emphasize is the fact that this is called a pole. When you have a pole, there are two distinct ends, just like how, and we can apply that idea to this one. This magnet here has two di ends. So this pole has two distinct ends. It has a partial negative end, and then it has a partial positive end. So this one, we can describe it as a dipole because, again, two distinct ends to this particular pole. We're contrasting it with this one, which doesn't have two distinct ends. And when I say distinct, I mean distinct charges. If you look at this one, and if you want to scrutinize it for its characteristic as a magnet, it is a very poor magnet because this end here is not distinct from this end right there. There's no charge difference. You don't get partial charges, you don't get full charges. You have a very boring uniformity average about this hydrogen to hydrogen molecule. So this one is a dipole. But I'm kind of jumping ahead of myself. It is also called a polar bond. You know, North and South Pole. Isn't that nice when vocabulary comes back and it kind of makes sense? So this is referred to as a polar bond. Polar bond because, again, you have distinct charges on those situations. Partial plus and then partial minus. Earth pole, dipole, polar bond because this electron tug of war between hydrogen and fluorine. Fluorine is super greedy, so it quote-unquote wins the electron tug of war on average more often than hydrogen. Way more often than hydrogen. So electron density builds up on one side, thereby creating this distinct end that's partially negative. Again, not a full negative, only a partial negative. So there it is. So far, we have a clear difference in electron quote-unquote sharing. Which again, that's why I don't like you to use the word sharing, because I would not describe this as sharing. This one, I guess you could call that sharing. It's a very equal sharing, and this one is a very unequal quote-unquote sharing. Just call it an overlap, please. So we have overlap of electron cloud densities that shifted more over to one side, creating a polar situation, non-polar situation. Alright, and of course this has some pretty important implications. So we just looked at individual molecules, but individual molecules are never alone in the world. There are always other molecules floating around in space. So therefore, if you have hydrogen and fluorine covalently bonded right here, and then you have another hydrogen and a fluorine bonded over there, think about what's happening with the polarities. So this hydrogen, this fluorine right here, fluorine has a slight buildup of negativity. And this fluorine here also has a slight buildup of negative because, again, fluorine is the greediest one. And it's much greedier than hydrogen. So it drains more electrons over to the fluorine side, and the hydrogen is slightly exposed if you compare it to the periodic table hydrogen again. So we're going to put some symbolic notation. So this is a partial positive. That fluorine right there is a partial negative. And same is true for this one. Partial positive. And then we have partial negative. Nice. Think about it as bar magnets, please. So if you have bar magnet number 1, that's a north and south end dipole. Dipole number 1, and then you have bar magnet number 2, which is also a dipole. So you have a dipole here, and then you have a dipole there. And since opposites attract following one of our first rules, negative is attracted to positive, they are in fact attracted, sticking kind of like bar magnets pretty much. And you know what some people call this? A very creative name. It's called a dipole-dipole. How creative, just like the strong force, right? Dipole-dipole, that is when you have one dipole that's attracted to the partial charges of another dipole, and then that one, because they stick together in this transient fashion, we call it a dipole moment in time. And again, the dipoles arise from the unequal distribution of electron cloud densities because of the unequal electronegativities between the atoms. So there we go. Dipole-dipole moment. Nice. So that one is pretty strong, but be careful. Don't conflate this as a type of bond. Do not call this a bond, please. This is just called something called an intermolecular force, IMF. So this is referred to as intermolecular force. If you break down the word, inter is between separate entities, and then M is molecule, of course. Molecular. And then force is just a very generic word to mean some sort of attractive thing, keeping things together. So there is a force between separate molecules, and that's how these two separate HF molecules are attracted together temporarily in space and time. But it's a very short-lived situation. They simply separate and continue on their own merry ways. They can be broken up, yes. This is, we'll talk about maybe freezing if we have time, but for now, that's going to be the dipole discussion. It's called intermolecular force. This is actually, let me clarify the vocabulary just a little bit. This is a dipole-dipole interaction. If you want to be generic, you don't call it a moment. If you want to be super generic, just call everything an interaction. All temporary things that happen between two separate molecules. You just call it an interaction, just to be as generic as possible. Dipole-dipole interaction. And the dipole-dipole interaction is itself a subcategory of intermolecular force. There are multiple types of intermolecular forces. But I guess we should cover those in brief. But let me clear this. Okay. So, just to elucidate the differences in between vocabulary words, we have bonds. We have chemical bonds, which specifically refer to these three main things. We have covalent, which I'm pretty sure I've beaten to death about it being overlap of the electron cloud densities that are stabilized between two nuclei at least, and then that's covalent. And then we have ionic, and you have full transfer, full stealing of electrons. And then we have metallic, which is where electron cloud densities are free to travel across amongst multiple nuclei. So those are bonds. Those are referred to as chemical bonds. So when you do reactions, you are essentially dealing with the making and breaking of these type of bonds. So these ones, when you look at chemistry and you do chemical reactions, these ones are the ones that we're talking about. Those are reactions. We're contrasting it with IMF's intermolecular forces, or some people call these ones interparticle forces. And we also have a list of those ones. There's a tier list. For this one, we have the S rank, we have the A rank, we have the B rank, and then we have the D rank. So in the S rank, we have ion dipole intermolecular forces, ion dipole. And then in the A rank, we have dipole-dipole. But there's a specific dipole-dipole that people like to single out, and they're called hydrogen bonds. Don't worry about that one just yet. But hydrogen bonds are just simply, they're not really bonds. They're not these ones right here. They just feel like it sometimes, maybe. But hydrogen bonds, and then below that one we have dipole-dipole. But the hydrogen bonds are actually just a subclass of the dipole-dipole. So I'm going to rewrite that. So A rank / B rank is going to be dipole-dipole. But because hydrogen bonds are so special and they show up a lot in biology, we can call that one the special type hydrogen bond, special type of dipole-dipole. They're pretty darn strong. They're not quote unquote permanent like these ones, but they're pretty darn strong. And then lastly, on the D list, on the SAD tier list, we have D, which will be something called van der Waals or something. I forgot how to pronounce this. Van der Waals? It's like Dutch, I believe. Van der Waals, you know, this is when scientists name it after themselves, or some other scientist names it after another scientist, since they're so important. They feel like they should honor the other scientist. So this name isn't that useful. So some other people instead of calling it Van der Waals, some people call it London dispersion, which is still named after someone. But at least it has the word dispersion. Running out of space. Hold on. Oh, this writing is atrocious. Whoops. London dispersion. Whoops. Okay. These are called the intermolecular forces or interparticle forces. They are not what we're talking about when we talk about chemical reactions in chemistry. We're talking about those three things. If you want to be more grammatically consistent, we can call these ones intramolecular bonds or forces. Intra meaning within the same molecule, within the same entity. So intra is within the same entity. So these bonds, we're looking at a particular molecule. This one is inter, that's between separate entities of molecules. Hence the word inter, the prefix inter. Okay, which is leading to the discussion of water, because water is oh so important for a lot of topics, including chemistry, including biology. Very important stuff. So let's go back. We have H2O, water. That is the chemical formula. But when you map it out in terms of a simple diagram, we call this one a Lewis structure. It looks crudely drawn like this. This represents a covalent bond. This represents a covalent bond. So when we're talking about this, let me do the cloud formation. We have oxygen, which has electron density around it, and then we have hydrogen, which also has electron cloud density. But again, because oxygen is greedier than the hydrogens, either of these two hydrogens, it could suck up the electron cloud density to a degree from those two hydrogens. So yeah, it has a lot more electron cloud density than either of those hydrogens. And because of that, we can assign the oxygen a partial negative charge. Right there. And then the hydrogens will give a partial positive charge, because compared to the periodic table value, they have slightly less electron cloud density. So there it is. So we wouldn't say that the hydrogens have, they always have one proton, but we can't say it has one full electron, but rather it has like 0. And I'm going to be making up the number here. I don't remember what the number is, but let's pretend it's 0.71. So I'm just trying to say that this is not a full -1. It's only a partial minus. And because it's partially minus, if you add it to +1, you get an overall positive that's less than 1. And that's why we call it a partial positive charge, because the plus is less than 1. Well, we don't need that visually. So here is water. There's a water molecule. And just to put up some of these labels, we call this bond is a covalent bond. And because if we focus our eyeball on this particular interaction between these two atoms specifically, because oxygen is greedier, has a higher electronegativity than does hydrogen, it's unequal distribution. So we call this one a polar. Remember, north and south pole, two distinct ends to a molecule. So these ones, if you look at it as a magnet, it has two distinct ends because of this partial negative and this partial positive. So we can call this one a polar covalent bond. And the same is true for this one, since it's virtually identical to this one. So polar covalent, polar covalent. Alright, and because this is a polar covalent bond, it behaves like a magnet, which is relevant if you have another water molecule. So suppose we have water molecule number 2, which also has the partial charges on that one. So for that water molecule, we do have a partial negative on the oxygen and a partial positive on the hydrogen. And because we have these partial charges that are opposite signs, we can conclude that they're going to attract each other following the basic magnetic rules. So thus, we get this interaction between them. And remember, you don't call this one a bond. This is only an attraction between two partial charges. It's not an overlap of electron density between two nuclei that are stabilized, quote unquote, permanently. This is only a transient interaction. This is again going back to the intermolecular force. It's an IMF. Broadly speaking, if we were to name this one more specifically, we would name it as a dipole-dipole. But because this dipole-dipole involves a hydrogen that's flanked by two very greedy, very partially negative atoms, we call it specifically a hydrogen bond. It's not a true bond, we just call it a bond for some reason, because it's like the hydrogen is bonding those two oxygens together. But remember, it's not a true bond. Okay, so if you were to name this one specifically, please call it a hydrogen bond. You are technically correct if you call it a dipole-dipole. You are technically correct if you call it intermolecular force, but for full credit, you would call it a hydrogen bond. Alright, so you have water molecule number 1 and you have water molecule number 2. Those are two separate molecules. Polar covalent happens within one molecule, so it's an intramolecular bond. So it's called, just called a covalent bond. This one, this purple thing between those two is happening between two separate molecular entities. So we call it intermolecular force, not a true bond. Alright, and then I think I'm going to wrap this up. If I go more into this topic, I'll probably go on to water, probably discussing more properties of water, you know, if like why you have solid formation. We're talking about melting and freezing of ice or water. Why do we have ice formation? Why do we have crystalline formation for water molecules? Why do we have a lower density for ice? What happens when you squish ice? You know, all this fun stuff. Probably next time. Who knows when that's going to be. When the mood strikes me, I guess. But that'll be it for today. Thank you for showing up, maybe watching this video. I have no idea. I will probably see you in the next one. Have a good day, or evening, or whatever. And that's it. Thank you.